Okay, we're just going to work a couple of more examples on integration by parts. Here's one where I'm going to work a definite integral. We can rewrite this as tan inverse. Arctan and tan inverse are the same things. Lots of students would rather see it in this form. So again, we are going to use integration by parts. So we need to find u. By default, whatever's left is going to be dv. Well, our two functions here are tan inverse of x and dx. So u has to be tan inverse of x because we're taking the derivative of it. And so dv is going to have to be dx. So the derivative of tan inverse, if you remember, this is u over a, so that's x over 1. So it's 1 over 1 squared plus x squared dx. And the antiderivative of dx, of course, is x. So our antiderivative function is u times v, so x times the tan inverse of x, minus the integral of v du. So that's x times 1 over 1 plus x squared dx. Well, I'm going to go ahead and write it like that. Hopefully by now you can recognize a u substitution when you see one. This is just a straightforward u substitution. This is not integration by parts, it's a u substitution. So I'm going to pick the denominator to be u. Du is therefore 2x dx, taking the derivative of my u. So this integral can be equivalently written as 1/2 the integral of 1 over u du. And the antiderivative would look like so, right? So we'll go back and we'll pick up the other part of our antiderivative function, x times the tan inverse of x minus 1/2 the natural log, and u was 1 plus x squared. So there's our antiderivative function. Instead of putting a plus c, we are going to use fundamental theorem. So this definite integral is 1 times the tan inverse of 1 minus 1/2 the natural log of 1 plus 1 squared. There's our upper limit, minus our lower limit is 0, and 0 times the tan inverse of 0 is still 0, minus 1/2 the natural log of 1 plus 0 squared. This cleans up to be the natural log of 1, which is 0. So that whole second term is 0. So here, the definite integral is the tan inverse of 1, not of thin air, minus 1/2 the natural log of 2. And we can come over here, I'll get a different color. Remember the theta measure where tangent equals 1 is pi over 4. We don't leave trig functions in our answers for fundamental theorem. So this is pi over 4 minus 1/2 natural log of 2. And that's a real number value. All right, so there's an example. I have one more example to do, and we'll finish up integration by parts. Now, this requires repeated integration by parts. Neither one of our functions, e to the x nor cosine of x, differentiate down to 0. So we're not going to be able to use Escalante's shortcut. Sometimes this is called solving for the unknown integral, and you'll see here in a minute why it's called that. So again, we want to fall back on our good old buddy LIPET. And LIPET, because we have an exponential function and a trig function, there's our exponential function, there's our trig function. LIPET tells us that u is going to need to be e to the x. Therefore, dv would be cosine of x dx. du is e to the x dx. Remember, e to the x is its own derivative. And v is going to be positive sine of x. So the integral of e to the x times cosine of x dx is u times v minus the integral of v du. So again, do you see we have another integration by parts? So we're going to just copy down e to the x times the cosine of x dx equals e to the x times the sine of x minus, now over here, LIPET tells us u needs to be e to the x again, dv has to be sine of x dx, so we're in good shape there. Du once again is e to the x dx, and v, this time what did I take the derivative of to get positive sine? That had to be negative cosine. Really watch your SIGN signs here. All right, so I have u times v. What I'm going to write right in here, and I'll write it in blue so we can keep up with it. I have negative e to the x times cosine of x. That is u times v. Minus the integral. Look at all these negatives. This negative is going to come over here and affect that negative. So it's v du. So I have another negative e to the x cosine of x dx. And look here again, I have another integration by parts. So let me just get another color here, and let's kind of start fresh and see what we've got going on. So e to the x times the sine of x. This negative and this negative make this term positive, so that's plus e to the x times cosine of x. This negative, and this negative make that integral negative. So there, that kind of sort of cleans everything up a little bit where we can see what's going on. Do you notice anything? I see some familiar things here. Look here. Does that look familiar? I'm in this infinite loop. I'm stuck right back where I started from. Is it going to do me any good to find u and dv and then v and du and do integration by parts? No, because I'm going to wind up right here again with just a few more terms in between. So what do we do now? What do we do when we have an unknown integral like this? Well, what we do is we bring algebra. So if I have the same, I'm going to try to get rid of that blue writing there so you can see what we're doing. I have like terms. Let's talk about this whole integral on the left-hand side of our equal sign being a term, and I have the exact same term being subtracted on the right-hand side of the equal sign. So if I was to add this on both sides of the equal sign, if I was to add the entire integral, that's going to go to 0, and I'm going to have two of those integrals over here. And look at the brilliance of that, because look what then is happening on the right-hand side of the equal sign. I have an antiderivative function. Now that antiderivative function is for 2 times that integral that I started with. Remember, this is what I'm trying to solve for. So I'm just going to divide both sides by 2. And the result will be the integral that they ask me to find the antiderivative for. So it will be half of that antiderivative function that's on the right side of the equal sign here. And my plus c, even when I distribute that 1/2, will still give me an arbitrary constant. So sometimes we can use Escalante's shortcut. The biggest clue there is that one of our functions are going to integrate down to 0. But if we have repeated derivatives and antiderivatives in our functions, and this happens a lot with exponentials and trigs, we could get caught in this infinite loop and keep doing repeated integration by parts over and over and over again. So if that happens, if you keep getting integrals that are of the same general form that you started with, look for your original integral to show back up. Keep looking for that unknown integral, or keep looking for that integral that you started with, and hopefully it's being subtracted, because then you can add it. See how important distributing this negative all the way over there? Because if you had written that as a positive value, you wouldn't have seen, you would have tried to subtract that from both sides, and you would have wound up with this equals 0, and that would have, given you some issues. So we have to be meticulous about everything, not just our calculus, but our algebra as well. So come to class next time and we'll do some practice on definite integrals and on these repeated integration by parts, and also getting mapped back to your original integral and getting in an infinite loop and knowing what to do with that. So come to class next time and we'll work some homework problems.